All right, so Calculus 30 lesson today is 3.5 related rates. Now, we've done lots of examples using derivatives recently of trig functions. We've optimized lots of things here. This is a different type of problem where instead of finding the instantaneous rate of change of one quantity with respect to the other, so derivative of y with respect to x in maximization or whatever that is, now we're dealing with multiple rates of change at once. Okay, rates that will be related somehow. So in real life situations, it's hard to examine one rate of change while keeping all other quantities constant, right? So there are lots of times where the change of one thing affects the other. So as explained in the book here, it says in a related rates problem, we're given the rate of change of one quantity, and we are asked to find the rate of change of a related quantity. So again, the two quantities will be related somehow. That's important. That's going to be important in the process of trying to solve all this. That's why these rates are related rates. To do this, we find an equation that relates the two quantities, and we use the chain rule to differentiate both sides of the equation with respect to time. Now, I do have some steps under here that we're going to follow as we do this example 1. So these steps will be rewritten down here, and I do a little more detail, I think. But the other thing that's important is we are going to differentiate with respect to time. In most cases, we are not going to differentiate with respect to one of the quantities that we're given or asked to find. We're going to differentiate with respect to a third quantity, and this would be time. Now, we're coming back to 3.5 here because we did 7.4 just recently, where we did the trig differentiation application section, right? And so we had x as part of a triangle, y part of a triangle, and we wrote x and y in terms of theta, the right triangle. So that was like a third variable, right? So that leads into this sort of thing where we are going to have to represent, or we're at least going to have to differentiate with respect to a third variable, okay? So anyways, as we work through this, you'll sort of hopefully understand what's happening. So example 1, let's focus on example 1 and what this looks like. Okay, it says this. A spherical balloon, this is not a balloon one. A spherical snowball is melting in such a way that its volume is decreasing at a rate of 1 cubic centimeter per minute. A snowball, it's melting, okay? It's winter out here right now. You can picture a snowball. It's sitting out there in the sun, and it's melting. And so what's happening to the snowball is the sphere, the ball, is decreasing in every dimension, right? It's melting this way. It's not one side, not melting to a half. It's shrinking in size like this, right? So its volume is decreasing at this rate. The question is, at what rate is the radius decreasing when the radius is 5 centimeters? So this question is loaded. A lot of the questions will look very similar to this, so I'm just going to break this question down for you and show you the parts that you need to focus on in order to solve these questions. So we are given a rate, okay? And what rate are we given? We are given the rate of change of the volume of a sphere. So this is what you're going to do. You're going to write down what you're given. So volume. Now, we don't know what the volume is, but we are given the rate of change of the volume. So that's actually the derivative of the volume, right? The volume is decreasing. That's a negative rate of change. It's decreasing. And the signs, positive, negative, are going to be pretty important here, okay? So if something is decreasing in size or decreasing in rate, make sure it's a negative. Now, the rate of change is 1 cubic centimeter per minute. So what you want to, I wouldn't suggest put the units in, work with the units in the question. Forget the units. For now, all we have to do is make sure that the units are lining up. So for example, this is cubic centimeters. We're given centimeters in the question. That's important, okay? If one of this was meters and one of them was centimeters, then we'd have to do some adjustment. But the important thing is that units line up, A, and B, you just take special note for the end of the question what the other units are. So this is minutes. We're dealing with time in minutes. Okay, so when we restate our answer, you have to include all this information. But I wouldn't put it in with the work. Okay, so we're given volume, the rate of change is decreasing. That's volume v prime is -1. We are asked to find the rate at which the radius is decreasing. So guess what? We don't know r prime. That's the rate of change of the radius. We don't know r prime. But I'm asked to find r prime, and here's the third part, okay? This is changing. The snowball's melting, okay? And you can probably picture this snowball. I don't have a snowball. But I'm going to make a snowball, an imaginary one, with my hands. And as the volume is decreasing, you can tell that the radius inside the snowball is also decreasing, right? So that makes sense. Volume is decreasing, so is the radius. Okay. Now, if the snowball was super huge like this, super huge and big, and the volume was decreasing, okay, at a rate, the radius would be decreasing at a rate. But as the snowball got smaller, you might be able to envision that the decrease in the radius might actually go either quicker or smaller as the volume is different. So the rate of change is not constant throughout the whole process. Okay? All right? If the snowball is big, the volume is going to change pretty slow. Compared to if the snowball was small, that volume is actually probably going to change quite a bit more, right? Because it's small and it's getting smaller and smaller and smaller. And all of a sudden, boom, you go from a volume to zero really quick, it seems. But this big snowball can take a long time, right, Jamel? So you have to know at what point are you looking for this rate of change. And that's the third most really important thing. So when the radius is 5 centimeters, and so I always do this, at r equals 5. All right? Now, this is going to be later in the question, okay? You're going to save this for later in the question, okay? Too many students put r equals 5 in at the beginning of the question, and then you run into trouble. And then nothing makes sense. So this is going to be later in the question, and you'll find out exactly what I mean here in a second. So we write down what we're given, write down at what point we are looking for this particular rate of change. And it's when the radius is 5. So what's the instantaneous rate of change of the radius when the radius is exactly 5 centimeters, exactly now? Okay? So we need a snapshot in time in order to find, to know what we're looking for. So here's the steps. Okay, moving on. Determine an equation that relates the two quantities only. Okay, so an equation that relates V and R. Well, as soon as we're talking about a sphere, that one's pretty easy, right? And a lot of these will be fairly straightforward. Volume of a sphere, okay? A sphere. Okay, I'll just put S there. I know how to spell sphere. S-P-H, okay. Volume of a sphere is what? Remember that? Please, somebody tell me you remember that. 3 over 4. Not quite. 4 over 3. 4 over 3. Pi r cubed. Right. R cubed, volume cubed. Okay. All right. Ooh, shake the dust off there. Okay, volume of a sphere, 4/3 pi r cubed. Now, notice, whoa, this is our equation right here. V and R. Boom. Step 1's taken care of. Okay. The different questions, you'll have different formulas. You might have to use Pythagoras. You might have to use trig. You might have to use, okay? Relate the two quantities involved. Now we take the derivative of the equation. And the derivative is going to be with respect to, as I mentioned before, with respect to time, okay?
Just a reminder to all support staff that time.
So this is the derivative with respect to time. Okay? Now, that means, what that means is that V is not our preferred variable. It's not on the bottom here. Okay? And really, R is not our preferred variable. So we are taking the derivative of V, yes, but it's with respect to time. So in a sense, this is okay, but don't mistake V for the preferred variable, if you know what I mean. Derivative of V is not 1 here. Okay? Derivative of V is V prime. The derivative of R is not 1. The derivative of R is R prime. Because our preferred variable is t. It's not in there, but we're taking the derivative of this equation, this whole thing, with respect to time. A third variable that's not really included. So all that means is that the derivative here, we implicitly differentiate. That's v prime equals, now 4/3 in pi, that's just a constant. So really we have this constant times r cubed, right? So we're going to do the power rule. 3 times 4/3 pi times r squared. So we're taking the derivative of the right side with respect to time, which means that at the end, when it's all said and done, I have to multiply by r prime. Chain rule. Okay? Chain rule. So the derivative of the variables, none of the variables, derivative is not 1. Okay? Just remember that. And it kind of makes sense, right? Because look at, I'm given v prime, I'm asking to find r prime, so they have to be in there somewhere. All right, so take the derivative of the equation, both sides implicit with chain. Good. 3. Now we substitute the values from the question and solve for the missing rate, including this one right here. So now we're saying, okay, at this point, the volume is decreasing at this rate. It's constant throughout, actually. So this one is not. It's constant throughout. The volume is decreasing at a certain rate. So that one is okay. Just to plug that in. Okay, it's -1. R we don't know, but r prime we don't know, but r we do. So this is what it looks like. It looks like a -1 over here. Those 3's are gone. This is going to be 4 times pi times 5 squared. See that? Okay, r is 5 times r prime. So r prime is -1 over 1 times 4, 100 pi. All right. That's what r prime is. So we've put everything in. We've solved for r prime. This is a pretty straightforward example. There's not a lot of fancy things we need to do. And other examples, we'll have to dig a little bit deeper. But basically, while this snowball is changing, okay, the rate is changing, and it's given in this question that the rate is changing at the exact same rate the whole time. So that's good. But the radius is changing at this rate. So you finish off with this sentence, radius is changing at a rate of -1 over 100 pi, and that's totally fine, just leave it like that. Now, what are the units here? So look back to the question. The radius is just a length. What's the length involved in the question? Centimeters. But this is with respect to time, right? Because really, this is dr with respect to time, right? So this is dv with respect to time. This is actually dr with respect to time, right? If you look at Leibniz. So with respect to time, centimeters per what? What's our time? Minute. Okay? And that's your answer for that question. Okay, so that's your intro and your first example for related rates. We're going to be given a rate, asked to find another rate, given a certain constraint or a certain point in time when we need to find this unknown rate, and then these are the steps you follow.